The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay? So, I thought I'd quickly list the four central topics for the Fourier part of the course, and I would guess that there'll be a question on each of those four in the final final exam. And we covered 4.1, Fourier series. I don't plan to do discussion in 4.2 of other series like Bessel and Legendre and so on. If I can, I'll come back to those in the very last lectures. But I want to pick up now on the second key example, which is the discrete Fourier series that has only n terms instead of this series, as you're looking at it, has infinitely many terms, but I'm going to cut back to n terms. So this k, well, I could go 1 to n, but the best way is 0 to n minus 1. So that's the discrete series. We're going to be dealing with a vector, c0 up to cn minus 1, and a vector of function values, vector to vector. So a matrix is going to be the key to everything here, an n by n matrix. So that's what's coming. Then after that, probably by Friday, will be the integral transform, and early next week and a little after Thanksgiving will be this key idea of convolution, which is really important in so many applications and needs to be separated out. Convolution will apply to all of these, and you'll see the point there. Okay, ready for the idea of the discrete one. Okay, so the key idea is we only have n terms, so I can't expect to reproduce a whole function. I can get n function values. So I'll get this at n different points. And if I'm thinking of my f of x on, let me take 0 to 2 pi now, and I'm thinking again of an f of x that's periodic. So it goes, it does whatever. If it was like that, if that was my f of x, just to remember about Fourier series, what could you tell me about the Fourier series for that f of x? Well, when I continue periodically, am I going to see a jump? Yes. There'll be a jump at every 2 pi. So the underlying function is not continuous, has a jump, so that our special examples with jumps and slow decay, 1 over k decay rate for the Fourier coefficients would apply here. Okay, that's remembering Fourier series. Now, Fourier integrals, I'm just going to take, let me just take n equal 4. So I'll take this point. You know what 4 points am I going to take? I'm not going to repeat. Let's make it. Let's just for the heck of it, make it look periodic. Yeah, let's make it look periodic. I never should have done it otherwise. Okay, okay, so there's 1 point. I'm just going to take four equally spaced being key. 0, 1, 2, 3. So n minus 1 is 3. And these values, 4 values I can get right. So those are my 4 x's, the 4 x's that I'm going to take. So this is x equals 0, of course. And this one is, what's the x there? X is 2 pi, the whole deal, the whole interval, but it's divided into n pieces, so 2 pi over n. So we are going to see a lot of fractions involving pi over n, or 2 pi over n. They're just going to come up everywhere because that's the delta x, the delta, the h, the step in the discrete form. Okay, so those are the x's. So I'm only going to get this at x equals 0, 2 pi over n, 4 pi over n, up to, whatever it comes out to, n minus 1, 2 pi over n. It's, that doesn't look elegant, so we probably will try to avoid writing that again. But this was the 3 times 2 pi over 4 that got us to there. So this is 2 pi over 8, pi over 4, 2 pi over 4, 4 pi over 4, 6 pi, okay. So we're only going to get equality at those x's. So it's those x's that I should plug in here. Okay, so let me do that. Let me plug in, what does this series look like at these 4 points? Yeah, let me see. Writing out all 4 equations, f at 0 is going to match the right side at 0 because 0 is one of my points. So I get C0 plus C1 plus C2 plus C3. Well, at x equals 0, right? All the e to these whatevers were 1. Now, at the next x, 2 pi over n, now I'm matching the series with a function at that value there, 2 pi over n. So now I have k equals 0. So what does k equals 0 give me? When k is 0, what's my term look like? It's just C0 times 1. Because if k is 0, e to the whatever is again 1. So this is just C0. Now here's the key. What is that business there at x equal 2 pi over n? Here comes the important number in this whole business. The important number in this whole business is, I'll call it w, is e to the 2 pi I over n. That's a complex number, and we'll place it in the complex plane. So you must get to know that number, w. Because when I plug in x equal, k is now 1 here, so I have C1 times this e to the I 1, 2 pi over n. What is that? W. So it's w C1. And what do I get from the next term in this series? I have C2, e to the I 2 x. X is 2 pi over n. Do you see what's happening? W squared is e to the 4 pi I over n. We're using the beauty of exponentials. That's what making everything go. It's w squared. And this guy will be w cubed, C3. That's the series at our points. And I'll write, so this is like, we'll just see this once, what were we doing, but this is what we're going to live with here. So I'll rewrite it all in terms of w. So you got the idea of what are we doing? We're matching at n points, and now we get the good notation w. Okay, and the next point, 4 pi over n. Well, again, k equals 0 term, it's just C0. The k equal 1 term, yeah, can you tell me what I get when k is 1? I have something times C1. It's e to the I 1, 4 pi over n. What's that? W squared. E to the I 4 pi over n is w squared. Look, this matrix is coming out symmetric. And this will be w to the 4th, and that'll turn out to be w to the 6th. And then the last row of the matrix is going to come from matching at 6 pi over n. And it will turn out to be C0, and it'll be w cubed w to the 6th, and w to the 9th. So I did the last row or two a bit fast, just because the pattern's there and you'll spot it. Now I want to pull out of that the matrix, the Fourier matrix, the 4 by 4 Fourier matrix that multiplies the C's and gives me the F's. Let me call these numbers y0, y1, y2, and y3, just to have a, so it's a vector of values of the function, and this is a vector of coefficients. So it's y's, the Fourier transform goes between y's and c's and y's, right? Connects a vector and all these guys. This is n values, n function values in physical space. These are n coefficients in frequency space. And one way is the discrete Fourier transform, and the other way is the inverse discrete Fourier transform. So, and it's a little bit confused which is which, actually. There was no question with Fourier series. It was easy to tell the function from the coefficients, because the function was f of x and the coefficients were a bunch of numbers. Here we only have n numbers, n y's and n c's, and we're transforming back and forth. But I'm finding right now the matrix, this Fourier matrix, is going to take the c's and give me the y's. So I'm talking here about the matrix F. And let's see what F is. Can you just see what that was? Y0 to Y3 equals this matrix F, the 4 by 4 matrix, times C0 to C3. This is really the inverse DFT. It reconstructs the y's from the c's, or easier way to say that is add up the series. So that's the usual DFT is taking us, starting with the y's and giving us the c's. So that we have to, this would be the discrete Fourier transform. Take a function, produce its coefficients. The reverse step is take the coefficients, add up the series, get the function. So that's what F does. So I'm going to focus on F, which is the one that involves this W guy. Okay, can you peel off from here what the matrix F is, the Fourier matrix? Its first row is all ones. Its first column is all ones. And then it's 1 W, W squared, W cubed, W squared, W4, W6, W cubed, W6, and W9 to the 9th power. Okay, so it's made up of these powers of W, the 0, first, second, and third power, and then higher powers. But higher powers are all, let's draw a picture. Where is W? So this is the complex plane. Here's the real and here's the imaginary direction. And let me take n to be, here n was 4. Let me take n to be 8 in my picture just to have some, then I'll be able to spot the 4s and the 8s. If n is 8, where would W8 be? So W8 is meant to be the e to the 2 pi I over 8 now. Where's that? Where's that number in that picture? Is it on the circle? Absolutely. This discrete Fourier transform never gets off this circle. And in fact, it never gets off 8 points on the circle. which are the 8 equally spaced points. This says go 1/8 of the way of the whole way around, which will be here. So there's W8. When I square it, what's the square of W8? The angle, what happens to the angle when I multiply numbers? I add the exponents. Here, if I'm multiplying by itself, it'll double the exponent, double the angle. It'll be, there's there's W8 squared. So that point is W8 squared. And it's the same as W4 because it's 1/4 the way round. And what is that number in ordinary language? I. It's I, right? It's 1. It's on the unit circle at 90 degrees, and it's on the imaginary axis. It's just I. So all this here was I squared, I cubed. I squared, I fourth, I sixth. I cube, I 6, I 9. The 4x4 Fourier matrix is just powers of I. And the n by n, the 8x8 Fourier matrix is powers of W8. And let's find all the rest of the powers. So there's W8, W8 squared. Where's W8 cubed? Here. I multiply those guys. I add the angle. I'm out to here. Here's the 4th power. Here's the 5th power, 6th power, 7th power. And finally, we get to W8 to the 8th power, which is 1. Because if I take the 8th power here, I've got e to the 2 pi I, and that's 1. So that's the picture to remember. And while looking at that picture, could you tell me the sum of those 8 numbers? What do those 8 numbers add up to? So I'm just want to ask, what do one plus W up to W to the 7th, when I'm doing the 8th guy, adds up to? So the sum of those 8 numbers, well, I wouldn't ask the question if it didn't have a nice answer. 0. That's, of course, the usual answer in math. We do all this work and we get 0. But now, of course, the real math is y. I mean, I'm sorry that, yeah. So math is, you got equations, but then always there's that kicker, y. And why do they add up to 0 here? Can you see that? Why those 8 numbers would add to 0? Well, yeah. So what do these add up to? Just those 2 guys? 1 and -1 add to 0. That and that add to 0. I can pair them off. This and this add to 0. That and that add to 0. Yeah, so that's one way of seeing it. But actually, even if n was 3 or 5 or some odd number, and I had, so should I do the picture for n equal 3? Just a little, doesn't need a very big picture for n equal 3. So where would the roots be for n equal 3? One of them is always 1. These are the 3 cube roots of 1 that I'm going to draw. Those were the 8th roots of 1, because if I take any one of those numbers, its 8th power brings me back to 1. So where are these guys? So this is 3 numbers equally spaced around the circle. Where do you think they are? Well, it's got to be at 120 degrees, 240 degrees, and 360. Yeah. And again, those will add to 0. Yeah. Yeah, you can't pair them off because we got an odd number, but it's safely 0. We could see why. Okay. So this section, this topic, is all about that matrix. It's all about that 4x4 or n by n matrix, which has powers of W. Notice that the matrix hasn't got any zeros. Hasn't even got anything close to 0. All those numbers are on the unit circle. So multiplying by that matrix which is the same as adding up the Fourier series at the 4 points, doing this calculation, finding these y's from the c's, reconstructing the y's given the coefficients, has 16 terms, right? The matrix has got 16 entries. All the entries in the matrix are showing up here in powers of W. We've got 16 multiplications. Well, maybe a couple of them were easy, but basically 16 multiplications and additions. Pretty much n squared work. N squared work. And that that's not bad. Except if you want to do it a million times, right? Suppose we have a typical n might be 1024. So the matrix has then got is 1024 squared numbers, which is about 1 million. So if we have a matrix with 1 million entries, 1 million operations to do, and then we do it 1 million times, then it's getting up to money that Congress would give to the banks, probably. Yeah, whatever. Anyway, serious money, serious computing time. And the wonderful thing is that there is a faster way than n squared. There's a faster way to do these 16 terms than the obvious way. You might say, well, they're pretty nice, and they are, but they're nicer than you can know. I mean, nicer than you can see immediately. This matrix will break up into simple steps with lots of zeros in each step, and the final result is that instead of n squared, capital N squared, which is done the old-fashioned way, let's say, there's a fast Fourier transform. So the FFT, I should maybe find a better space. It's the most important algorithm in the last 100 years, and here it is. Right there. Oh, well. Well, I guess my goal, one goal for Wednesday will be to give you some insight into the FFT. But here I'm just looking at the result. The number of computations is, instead of n squared, it's n times log n. And it's log to the base 2, or maybe 1/2 n log n. So I'll erase some of the other things close by so you see it. So that, where n squared was, if n was 1,000, n squared was 1 million. If n is 1,000, this is 1,000, and what's the logarithm of 1,000 to the base 2? That's the 10, right? The 2 to the 10th gave us that 1,024. So this is 10 to the 4th. So n is 10 cubed. The logarithm, or 1,024 more exactly, the logarithm is 10. So we're 10 to the 4th instead of 10 to the 6th. And that's a saving of a factor of 100 that's true. I mean, it just comes from doing the addition and multiplication in the right order. You get this incredible saving. And it sort of makes whole calculations that were previously impossible are now possible, because it's, instead of where it might have been 100 minutes, it's now 1 minute. Okay. So everything focuses on this Fourier matrix and its inverse, which we still have to find, but it'll come out beautifully. In fact, I could tell you what F inverse, just so you see it coming. F inverse will, so what happened to W, that all-important number W? Well, let me repeat what W is. Okay, I guess we can. I'll put it on this board. F has powers of W. W is e to the 2 pi I over n. And what power has it got in the j, k position? So now you're going to see a formula for these entries. Only you have to let me start the count at j and k equals 0. This is a 0-based, where MATLAB is 1-based, and to do this stuff you always have to shift things by 1. Some other more recent software like Python is 0-based, because this is so common. So these ones for j, here's the formula. It's w to the power j times k. That's neat. That's what goes into the matrix F. Into this is here is row 3. It looks like row 4, but I'm starting with 0. So that's row 3. That's column 3. This is w 3 times 3, w the 9th, which, by the way, is the same as what? What is, if w is I in this 4 by 4, it is. W is I. What's w to the 9th? What's I to the 9th power? Same as, can you do I to the 9th in your head? Sure. Because you're starting here, you're taking its 9th power. So 1, 2, 3, 4, you're back to 1. I to the 4th is 1. 1, 2, 3, 4 more. I to the 8th is 1. I to the 9th. That will actually be just I. I to the 9th. So they're all powers of I. But this is the good way to see it. It's 3 times 3 because it's in, and this, of course, is 3 times 2 and 2 times 2 and 3 times 1. You see the entries of F. Yeah. So now I better write down, I promised to write this formula in a better form. All those formulas in a better, yeah, that's, nobody is going to write this out for matrix of order 1000, right? So we've got to write the decent formula. So the decent formula is that the jth y, because it's going to come in equation number j, will be the sum on k equals 0 to n minus 1 of ck times w to the jk. Those are the entries. Those are the c's that are multipliers and the y's that's a gift. This is just y, vector-wise, this is y equal fc. Yeah, now we finally got a good notation. So this was like horrible notation. I mean, that's like exhausting. This shows you the algebra, but you have to be sort of prepared. Well, the information is here because this is telling you what the entries of F of the matrix are. But like this is with indices, and this is with whole vectors. Right. So I would, that would be y. In MATLAB, that would be the inverse fast Fourier transform of C. So you see that that's our matrix. Okay. Now, I was going to say, before I show why, I was going to say, what about the inverse? Because if the FFT gave us a fast way to multiply by F, we want it also to give us a fast way to do the inverse, right? We have to go both ways here. We get our data, we put it into frequency space, we look at it in frequency space, we understand what's going on by separating out the frequencies. We maybe smooth it, we maybe convolve it, whatever we do, compress it, and then we got to go back to physical space. So we have to go both ways. And the question is, what about F inverse? And let me just say what goes into F inverse. The point is that the number that goes into F inverse is just like W but it's the complex conjugate, and I'll call it W bar. And that's e to the minus 2 pi I over n. So the thing that's going to go into the inverse matrix is the powers of W bar, the complex conjugate, JK. Let me just say right away that just as there were 2 pi's in the Fourier series world, that got in our way, and physicists can't stand those 2 pi's. They try to get rid of them, but of course they can't. They're there. But so they put it up into the exponent. Well, I guess I'm blaming physicists. I've done it too. I've put the 2 pi up there. For the Fourier series, anyway, whatever, 2 pi's are all in your hair in the Fourier series. And in this, for the discrete one, the corresponding thing is an n. There's a factor n that I have to deal with. Because, look. Yeah, here's what I'm saying. Here, let me multiply f by f inverse. Okay. Say 1, 1, 1, 1, 1, I squared, I cubed. This is my f, right? Whoops. Don't ever let me do that. I squared, 4th, 6th, I cubed, I 6, I 9. Now my claim is that f inverse is going to involve the complex conjugate, W bar, I bar. What is the complex conjugate of I? You see that we really have to use complex numbers here, but they're on the unit circle. You couldn't ask for better ones. What's the complex conjugate that's going to go into f inverse? If I take I and I take its conjugate, what does that mean? So the conjugate of that is just flip it across the real axis to the other one. Yeah, you see it's great. The complex conjugate of I is minus I. The complex conjugate, here's W8, here's W bar 8. It's just across the axis. So it still has size 1. And of course, it's e to this angle, which is just minus this angle. So that's why we get this minus. Because when I flip it across, I changes to minus I, angles changes to minus angles. And finally, I was going to do this multiplication just to see. So now I'm claiming that this is 1, 1, 1, 1, 1, 1, 1, minus I squared, minus I cubed, so on, minus I squared, minus I cubed, 4th, 6th, 6th, and 9. And now, if you do that multiplication, you will get the identity matrix. That's the great thing. You get the identity. 1, 1, 1, 1. Except for a factor n. Now, what happens when do you see that coming? When I multiply this by this, what do I get? 4. If they were n by n, I'd have n ones against n ones, so I'd have to expect an n there. Yeah. So f times f inverse, well, f times f inverse. So in other words, if I want to get the identity, I better divide this by n. So now I have, that's f inverse equal I. So f inverse is just like f, except complex conjugate and divide by n. So if I want this formula to be really correct, I have to divide by n. Okay. So and that's what W and W bar is. And another letter that often gets used in this topic is omega. And I figure that's a good way to separate out the complex conjugate. That's call this guy W and call this guy omega. So this is W and here's omega. I don't know if that helps. But you do have to keep straight whether you're talking about this number or that number. And this number could be called W because omega wouldn't be easy to type. So just you have to So you have to pay attention which one you're doing, and when somewhere you have to divide by n. But otherwise, it's fantastic. It's just beautiful. So if I write out yeah, I have to do that. Yeah. Can we do that multiplication? Just to see that it really works? Well, the ones worked fine. What about the ones times, what about the ones times that column? So I'm looking at the 1, 2 entry in this multiplication, or rather the 0, 1 entry, I should say. This is the 0th row, and this is the row number 1, and what do I get out of that? 0, right? That was my point, that this is adding up, going the other way around because it's the complex conjugate, but it's adding up the same four numbers and giving me that 0. And now how about the ones on the diagonal? When I do this times this, so this is the row times itself, what am I seeing there? What are these terms? That's certainly 1. What is I times minus I? I times minus I is 1 again. A number is getting multiplied by its conjugate. That gives you something real and positive when you multiply a number by its conjugate, a number by its conjugate. In fact, we get 1 every time, so we get 4 ones, we divide by 4, and we get that. Maybe you actually see here, just so you remember. So F inverse is, I'm concluding that F inverse, I'm looking now, what is F inverse? It's F conjugate divided by this nuisance number n. I could put square root of n with F, and then square root of n would show up with F inverse, just the way I could have done square root of 2 pi with one and square root of 2 pi with the other, but let's leave it like so. Yeah. So that's not proved in a way, just checked for a couple of cases with n equal 4, but it always works. So that's the beauty. In other words, the two directions, the y to c and the c to y, are both going to be speeded up by the FFT. The FFT, whatever it could do with w and powers of w, it can do the same with w bar and powers of w bar. If the FFT is a fast way to multiply by that, it'll also give me a fast way to multiply to do the other transform. Yeah, so the FFT is what makes this would all be important if the FFT didn't exist. And of course, actually, Fourier didn't notice it. Gauss again had the idea, but he had so many ideas it wasn't very clear in his notes, the FFT idea. But then Cooley and Tukey, guys at Bell Labs in the 1950s, discovered it in a small paper. I don't think they had any idea how important it would be. But they published their paper, and people saw what was happening and realized that that gave the right way to do the transforms. Okay, I was going to say here, do you notice that this 1, when I take a vector, that vector and its complex conjugate, what am I getting? I'm getting the length squared. I'm getting the right inner product. This is the right inner product when things are complex. Something times its conjugate. I'm just reminding you that the inner product of two vectors, u dot v or u comma v, should now be the sum. It used to be the sum of ui vi. But now we're in the complex case, so we should take the conjugate of one of them. And here, I guess that's the v, and this is the u. And so the point is that we're taking the right, yeah, we have, oh yeah, let me just say it this way. The columns, these columns are orthogonal. Those four columns, the columns of the Fourier matrix are orthogonal. In other words, we have an orthogonal basis. And it's those four columns. That's the, yeah, I almost missed saying that. But you remember from last week, the whole point about sines and cosines and exponentials in the function case was orthogonal. That's what made everything work, and it makes everything work here. Here we have vectors, not functions. Orthogonal just means dot products are 0. But they're complex, so that in the dot product, one factor or the other has to get conjugated. Anyway, that's an orthogonal matrix. Apart from this n, this capital N thing. So that's, if I normalize it, if I take out 1 over square root of n, now the length of every column is 1. So now I have orthonormal columns. 1 squared, 1 squared, 1 squared, 1 squared is 4. Divided by 4 is 1, and every column has length, is a vector in 4-dimensional complex space of length 1, and orthogonal. So that means orthonormal. It's a fantastic matrix. That's the best basis we'll ever have for complex 4-dimensional space, that basis. Well, actually, when I say the best basis we'll ever have, I realize I wrote a book about wavelets. And the idea of wavelets is there's another basis, a wavelet basis. And I hope to tell you about that at the very end of the semester. So wavelets would be another basis. Would you like to know the wavelet basis? Have we got? Yeah, just in case the end of the semester doesn't come. Can I write down here the wavelet basis? Okay. And you can decide you maybe like it better. So the 4x4 wavelet basis. All right. So this will be the wavelet matrix. Well, this was too good to lose, right? That's a terrific vector. All ones, constant vector. It's the thing that gives us the average. This C0 is going to, again, be the average of the y's. Yeah, it's just, yeah, how do I get that average? Yeah, somehow I'm doing, the C0, the constant term is, again, I'm going to take 1 of everything and I'll divide by 4 and I'll have the average. So I like that vector. That's the DC vector if I'm talking about direct current vector, if I'm talking about networks. It's in an image, it would be you could call it the blackboard vector. The whole image of an empty blackboard would be constants. Okay, so that's too good to lose. Now the obvious thing orthogonal to that would be 1, 1, minus 1, minus 1. Right, now I've got 2 orthogonal columns. And probably that's pretty close to something I have over here. Now, here's the point about wavelets. You'll see it with the next guy. The next one, you saw that those 2 are orthogonal and real and simple, nice numbers. Now, the next one will be 1, minus 1, 0, 0. Do you see that that's orthogonal? Obviously, because its dot product with that is 0 and that is 0. And you want to tell me the last column of the wavelet, of the simple wavelet matrix? This would be the Haar, named after Haar, the Haar wavelets. The whole point about wavelets was a new basis. Somebody realized, well, actually Haar lived a long time ago, but but they got improved and improved. But here's the simplest one. What's the good fourth column, fourth orthogonal vector here? What shall I start with? Zeros, and then I'll put 1 minus 1. So the beauty of wavelets is I've got this averaging vector, and then I've got this difference sort of on a big scale, and then I've got differences on a little scale with zeros, differences here with zeros. So as I keep going, I could do 8 by 8, 16 by 16. I get the averaging guy, and then I get I get large scale differences, and then I get finer differences, so coarse differences, finer differences, finer differences. And that's a really good way to, if your signal has jumps, we saw that Fourier wasn't perfect, right? And a lot of signals have jumps, right? If you're shocks, whatever you're trying to represent. This is a better basis to represent a jump, a discontinuity, than Fourier. Because Fourier at a discontinuity does its best, but it's not a local basis. It can't specially focus on that jump point, and the result is the coefficients decay very slowly, and it's hard to compute with. Whereas the wavelet is great for signals that have jumps, that something happens suddenly at a certain time. Anyway, that would be another, and of course I haven't made these unit vectors. I'd have to divide that by the square root of 4 and divide these guys by the square root of 2 just to normalize them. But normalizing isn't important. Orthogonal is what is important. Yeah. Okay. So that's the competition, you could say. That's the competition. Okay, back to the main guy. So this is the famous formula that gives the y's from the c's, and what's the other formula that gives the c's from the y's? So now this is the transform in the other direction. So it's going to be a sum from j equals 0 to n minus 1. And what's going to go in there? Have you got the idea of the two transforms? In one direction, this is e to the I. You see why we don't want to write it. That number is e to the 2 pi I j k over n. That's what that number is in the Fourier matrix. So you see, using W makes it much cleaner. Okay, what goes there? W bar. The complex conjugate, e to the minus all that stuff. W bar to the same power jk, and then I have to remember to divide by n somewhere. I can put it here, I can put it there, but I have the all ones vector has length squared equal to n, and I've got to divide by an n somewhere. Okay, those are the two formulas that many people would just remember. That for them, that's the discrete Fourier transform and the inverse, and maybe they would put the n over there. Probably that would be more common. I got started with the Fourier matrix with this side, and then the DFT matrix comes here, and I needed the n. So those are the formulas. I don't know how you prefer to remember these. I mean, somehow you have to commit something to memory here, certainly what W is, and the fact that it's W and W bar, and the fact that the sums start at 0, and the fact that you have just these simple expressions for the entries in the matrix, and this then would be C equals F inverse Y. That's what That's what I've written down there in detail. Okay, so that's the discrete Fourier transform, and I think we're out of time. I've got more to say in a little bit about the FFT, how that works.